When I talk about dark energy, I like to start from something simple and solid. The universe is expanding. That statement is not a metaphor. It is a quantitative measured fact. We know it from light. When we look at distant galaxies, we measure how their light is stretched. That stretching is called redshift. The farther a galaxy is, on average, the more its light is redshifted. This is the Hubble-Lemaître law. Velocity is proportional to distance. Space itself is expanding, and galaxies are carried along with that expansion. If gravity were the only major force acting on the large-scale universe, we would expect this expansion to slow down over time. Matter attracts matter. The combined gravity of all the matter in the universe should pull on everything else and gradually reduce the expansion rate. It could slow, but never stop, or slow and eventually reverse, depending on how much matter there is. That was the expectation for much of the 20th century. Cosmologists argued about whether the universe would expand forever or collapse in a big crunch, but most assumed the expansion rate was decreasing. In the late 1990s, two independent teams tried to measure how the expansion rate had changed over cosmic time. They used Type Ia supernovae as standard candles. These are exploding white dwarf stars that reach nearly the same peak brightness, so their apparent brightness tells us how far away they are. Combine that distance with their redshift, and you can reconstruct the expansion history. The results surprised almost everyone. Distant supernovae, which show us the universe as it was billions of years ago, appeared dimmer than expected. That meant they were farther away than a decelerating universe model predicted. The only way to make sense of the data was that the expansion of the universe had been speeding up, not slowing down, for the last several billion years. This accelerated expansion is what we attribute to dark energy. I use the word attribute carefully. Dark energy is not something we have directly detected in the lab. It is a name we give to whatever is causing the large-scale expansion of the universe to accelerate. We see its effect in the way distant supernovae look. We see it in the pattern of temperature fluctuations in the cosmic microwave background, the afterglow of the Big Bang. We see it in the statistics of how galaxies cluster on very large scales. All of these independent observations point to the same conclusion. About 68 to 70% of the total energy density of the universe today is in some form that acts like a smooth negative pressure component. That component drives accelerated expansion. To understand why we say negative pressure, I need to connect dark energy to general relativity. In Einstein's theory, gravity is not a force in the Newtonian sense. It is the curvature of spacetime caused by energy and momentum. The equations of general relativity, the Einstein field equations, tell us how the geometry of spacetime responds to the content of the universe. In this framework, not only mass but also pressure contributes to gravity. Positive pressure, like the pressure of a gas, adds to gravitational attraction. Negative pressure has the opposite effect in the Friedmann equations that describe an expanding universe. A component with sufficiently negative pressure can cause the expansion to accelerate. The simplest possible form of dark energy is a cosmological constant, usually written as Lil, lambda. Einstein originally introduced Lil as a term in his equations to allow a static universe. Later, after the discovery of cosmic expansion, he reportedly called it his biggest blunder, although the exact quote is debated. In modern cosmology, the cosmological constant has returned, but with a different role. It is interpreted as a constant energy density of the vacuum itself. In quantum field theory, even empty space is not truly empty. Fields have zero-point fluctuations. The vacuum has an energy. If that vacuum energy is constant in space and time, it acts like a cosmological constant. Its pressure is negative and equal in magnitude to its energy density, which leads to accelerated expansion. This Lil-CDM model, with EEL for dark energy and CDM for cold dark matter, is our standard cosmological model. It is simple and remarkably successful. It fits the cosmic microwave background power spectrum. It matches large-scale structure data. It is consistent with baryon acoustic oscillation measurements, which are like a fossil record of sound waves in the early universe imprinted in the distribution of galaxies. It reproduces the observed expansion history from supernovae. From all of this, we infer that the universe today is about 5% ordinary matter, about 25% dark matter, and about 70% dark energy. Dark matter and dark energy are very different. Dark matter clusters under gravity. It forms halos. It helps build galaxies and galaxy clusters. It behaves on large scales like a pressureless fluid that only interacts gravitationally. Dark energy does not seem to cluster significantly, at least not on scales smaller than the observable universe. It appears to be smooth, uniform, and persistent. Dark matter slows the expansion. Dark energy speeds it up. The cosmic expansion rate at any time is the result of this competition. In the early universe, matter and radiation dominated, so expansion slowed. As the universe expanded and matter thinned out, the relative importance of dark energy grew. A few billion years ago, dark energy began to dominate, and the expansion started to accelerate. How do we know dark energy is really there, and not just a misunderstanding of gravity on large scales? This is an active question. One possibility is that general relativity is not the full story on cosmological distances. Maybe gravity is weaker or behaves differently on scales of hundreds of millions of light years. Many modified gravity theories have been proposed. FR gravity, scalar tensor theories, brainworld models, and others. These aim to explain accelerated expansion without invoking a new energy component. But they must also match the precise pattern of cosmic microwave background anisotropies, the growth rate of structure, gravitational lensing measurements, and local tests of gravity in the solar system and binary pulsars. So far, the LICDM model with a cosmological constant fits the data at least as well as, and usually better than, these alternatives. That does not prove YEL is correct, but it makes it the benchmark model. We also measure dark energy through its effect on the growth of cosmic structure. Gravity tends to make overdense regions grow over time. Dark energy, by accelerating expansion, stretches space faster and makes it harder for gravity to pull matter together. So the presence of dark energy slows the growth of galaxy clusters and large-scale structure. We can measure how rapidly structure grows by looking at the distribution of galaxies at different redshifts by using weak gravitational lensing to map the distribution of mass, and by counting clusters. These growth measurements provide a check on the expansion history inferred from supernova and the cosmic microwave background. If the expansion is accelerating due to a smooth dark energy component, there is a specific way the growth rate should be suppressed. Observations so far are broadly consistent with that picture, although there are some tensions and uncertainties that are being studied. When I say dark energy has negative pressure, that is a statement about its equation of state. We usually write this as W equals P by Vruhr, where P is pressure and Vruhr is energy density. For non-relativistic matter, like cold dark matter or ordinary atoms at low speeds, dou is approximately 0. Pressure is negligible compared to energy density. For radiation, like photons, W is 1/3. For a cosmological constant, W is exactly -1. That value gives a constant energy density as the universe expands. If W is slightly different from -1, or if it changes with time, that would suggest dark energy is not a pure cosmological constant, but something more dynamic, like a scalar field often called quintessence. Measuring W and whether it evolves is one of the central goals of observational cosmology today. We use several techniques to constrain W. Type Ia supernovae give us the distance redshift relation. Baryon acoustic oscillations give us a standard ruler in the distribution of galaxies. Weak lensing maps the matter distribution and the geometry of space. Redshift space distortions tell us about the growth rate of structure. The cosmic microwave background provides a precise snapshot of the early universe and sets the overall framework. By combining all these, we can infer W. Current data are consistent with W very close to -1 within a few percent, and no strong evidence for time evolution. That keeps the cosmological constant hypothesis alive. But the error bars still allow the possibility of more complex dark energy. There is a deep theoretical problem with the cosmological constant idea. In quantum field theory, if we estimate the vacuum energy by summing the zero-point energies of all modes of all fields up to some high-energy cutoff, we get a huge value, many orders of magnitude larger than what we infer from cosmology. Depending on how you make the estimate, the discrepancy can be around 120 orders of magnitude. This is sometimes called the worst theoretical prediction in physics. Somehow, the observed vacuum energy is incredibly small compared to naive quantum field theory expectations, but not exactly zero. We do not know why. This is the cosmological constant problem. Dark energy, in this sense, is not only an observational puzzle, but a conceptual one. Dark energy also shapes the fate of the universe. In a matter-dominated universe without dark energy, the ultimate fate would depend mainly on the total density of matter and the curvature of space. If the density were above a critical value, expansion would eventually halt and reverse, leading to a big crunch. If it were below that value, expansion would go on forever, but slow down. With dark energy, the picture changes. If dark energy is a true cosmological constant with W equals -1, then the expansion will continue to accelerate forever. Distant galaxies will recede faster and faster. Over very long timescales, beyond tens or hundreds of billions of years, most galaxies will move beyond our cosmic horizon. Their light will never reach us. The observable universe will contain only our local gravitationally bound structures, like the Milky Way and the Andromeda Galaxy, which will likely merge, and their associated satellites. The universe as a whole will still exist and expand, but the region we can see and interact with will shrink in a practical sense. In that scenario, dark energy does not tear apart galaxies or solar systems. On the scales of galaxies and smaller, gravity is strong enough to hold structures together against the relatively gentle push of a cosmological constant. The accelerated expansion mainly affects the vast, low-density regions between galaxy clusters and superclusters. Over time, it stretches those regions faster than gravity can pull them back together. The large-scale cosmic web freezes in comoving coordinates, and structures stop merging significantly beyond a certain time. The universe becomes dominated by isolated island universes separated by ever-growing voids. If dark energy is not a cosmological constant, the fate of the universe could be different. If W is greater than -1 but still less than -1/3, dark energy would still drive acceleration, but its influence might weaken over time. In some models, dark energy could decay, or its energy density could decrease faster than a cosmological constant. In that case, matter could again dominate in the far future, changing the long-term evolution. On the other hand, if W is less than -1, we enter the regime often called phantom energy. In such models, the energy density of dark energy increases with time as the universe expands. The expansion accelerates more and more violently. In extreme cases, this leads to a big rip, where the scale factor of the universe diverges in a finite time. In that scenario, gravitationally bound structures could eventually be torn apart. First galaxy clusters, then galaxies, then solar systems, then even atoms, as the expansion overwhelms all binding forces. It is important to say that we do not have strong evidence that W is less than -1. Some analyses have hinted at values slightly below -1, but within uncertainties that still include -1. Systematic errors in observations can easily shift the inferred value of W by a small amount. So while the Big Rip is a logically possible outcome in some dark energy models, it is not a prediction we can make with confidence. Our current best fit model, LIL-CDM, predicts eternal accelerated expansion without a rip. Dark energy also interacts with dark matter and ordinary matter through gravity. It influences the way large-scale structure forms. In the early universe, when the cosmic microwave background was emitted, dark energy was negligible. Radiation and matter dominated the energy budget. The small fluctuations in density we see in the microwave background grew over billions of years into galaxies and clusters. As dark energy became important, it started to slow that growth. We can see this in the way the amplitude of matter fluctuations, often described by parameters like set8, evolves with redshift. Comparing the growth rate to the expansion history is a powerful way to test whether dark energy is a new component or a sign of modified gravity. If the relationship between expansion and growth does not match general relativity with a smooth dark energy, that would point to new physics in gravity itself. Gravitational lensing is another key tool. Massive structures bend light. By measuring the tiny distortions in the shapes of many distant galaxies, we can reconstruct the distribution of mass along the line of sight. This weak lensing signal depends on both the geometry of the universe and the growth of structure. Dark energy affects both. Large surveys, like those using the Dark Energy Survey, the Subaru Telescope, the Vera Rubin Observatory, Euclid, and the Nancy Grace Roman Space Telescope, are designed to map weak lensing over huge areas of the sky and over a range of redshifts. The goal is to measure dark energy's properties with high precision and to test for deviations from general relativity. There are also subtle tensions in our current cosmological data that might be hints of something interesting. One example is the so-called Hubble tension, measurements of the current expansion rate, the Hubble constant using the cosmic microwave background, and the LIL-CDM model give a value around 67 to 68 kilometers per second per megaparsec. Local measurements using Cepheid variables and Type 1a supernovae give a higher value, around 73 kilometers per second per megaparsec. This discrepancy is larger than the quoted uncertainties and has persisted as data have improved. It could be due to unknown systematics in one or both methods. It could also be a sign that our standard model is incomplete. Some proposed solutions involve changes in the early universe. Some involve evolving dark energy. None of these explanations is yet widely accepted, but the tension keeps pressure on our models. Another area of tension involves the amplitude of matter clustering, often summarized by the combination S8. Some weak lensing surveys find slightly lower values of S8 than those inferred from the cosmic microwave background under LIL-CDM. Again, the differences are not huge, and systematics are challenging. But if they hold up, they could hint that the growth of structure is suppressed compared to expectations, possibly due to some property of dark energy or a modification of gravity. On the theoretical side, many models of dark energy beyond the cosmological constant have been explored. Quintessence models involve a scalar field rolling slowly down a potential. The field's energy density and pressure can change over time, leading to an evolving W. There are K-essence models, where the kinetic term of the field is non-standard. There are coupled dark energy models, where dark energy interacts directly with dark matter. There are chameleon and screening mechanisms that allow modifications of gravity to be large on cosmological scales, but small in high-density environments like the solar system. Each of these models tries to address some aspect of the data or the cosmological constant problem, but they also introduce new parameters and new fine-tuning issues. As of now, none has the same combination of simplicity and empirical success as LIL-CDM. We should also remember that dark energy is not the only unknown in cosmology. Dark matter itself is not yet identified. We infer its existence from galaxy rotation curves, from gravitational lensing, from the cosmic microwave background, and from structure formation. It behaves like a cold, collisionless component, but we do not know what particle or particles make it up. The fact that about 95% of the energy content of the universe is in forms we do not fully understand is sobering. Dark energy and dark matter together form a framework that fits the data, but they also highlight gaps in our knowledge of fundamental physics. Despite these gaps, we can say some things with confidence. The universe is spatially very close to flat on large scales. The energy density is near the critical value. Dark energy currently dominates that energy density. The expansion of the universe is accelerating. The acceleration started a few billion years ago. Dark energy appears smooth and almost uniform. Its equation of state parameter W is close to -1. These are robust conclusions from multiple independent observations. In terms of space-time, dark energy changes the way we think about the large-scale geometry of the universe. In a matter-dominated universe, the expansion rate slows, and the Hubble radius, roughly the distance at which galaxies recede at the speed of light, grows faster than the scale factor. More and more of the universe becomes observable over time. In a dark energy-dominated universe with a cosmological constant, the expansion tends toward a de Sitter phase. The Hubble radius approaches a constant value. There is a cosmic event horizon, a finite distance, beyond which events can never influence us, no matter how long we wait. This horizon is not a solid boundary, but it is a limit in space-time. Dark energy, through its effect on the geometry, defines what parts of the universe are in causal contact in the far future. We can even think of the cosmological constant as giving space-time a kind of intrinsic curvature, even in the absence of matter. In de Sitter space, the vacuum solution of Einstein's equations with a positive L, space-time expands exponentially. That is similar in form to the inflationary phase we think occurred in the very early universe. Inflation is driven by an effective dark energy-like field with W close to -1. The difference is that inflation ended, reheated the universe, and gave way to a radiation and matter-dominated era. The current dark energy domination seems much more gentle and long-lasting. The similarity between early-time inflation and late-time acceleration raises questions. Are they related? Do they come from similar physics at different energy scales? Or is the resemblance superficial? We do not yet know. Even if dark energy is just a cosmological constant, its small but non-zero value is puzzling. Why is it not exactly zero? Why is it not enormous? Why is its energy density of the same order of magnitude as the current matter density, right now, in cosmic time? This is sometimes called the coincidence problem. Over the history of the universe, the matter density has dropped as the universe expanded, while a cosmological constant would stay the same. It is only in a relatively narrow window of time that they are comparable. We happen to live in that window. That could be a coincidence. It could have a deeper explanation. It could be related to selection effects in a multiverse, as some anthropic arguments suggest. But those ideas are speculative and not directly testable at present. From an empirical standpoint, we simply note the coincidence and treat it as a clue that our understanding is incomplete. Future observations will push these questions further. More precise supernova surveys, better measurements of baryon acoustic oscillations, deeper and wider weak lensing maps, and improved cosmic microwave background data will tighten constraints on W and its evolution. Gravitational wave standard sirens, like binary neutron star mergers with optical counterparts, provide an independent way to measure cosmic distances and the expansion rate. Cross-correlations between different probes will help control systematics. On the theory side, advances in particle physics, quantum gravity, and quantum field theory in curved spacetime may shed light on the cosmological constant problem and on possible dynamical dark energy models. In the end, dark energy is a placeholder name for a set of observed phenomena, accelerated expansion, a dominant smooth energy density, and specific geometric and growth signatures in the universe. We know it is there in the sense that our best models require it to match the data. We know some of its properties. It is nearly uniform. It has strong negative pressure, and it dominates the energy budget today. We know how it competes with gravity and dark matter to shape the cosmic expansion and the large-scale structure. We know how, in the standard picture, it will drive the universe toward a cold, dilute, and isolated future. But there is something we still do not know, and it is a simple question to state. Is dark energy truly a constant property of the vacuum with W exactly -1 and no time evolution? Or is it a dynamic field or modification of gravity that changes over cosmic time? That single question remains open, and the universe is our only laboratory to answer it.